friends, students and learners, I am Shashank Srivastava from School of Engineering and Technology under Gandhi National Open University, and now we are going to discuss a new unit, which is the unit number 4 of your block number 1, and it was entitled Smart Materials. This is a separate unit that has been added to this material science course to introduce you to the latest type of materials. And this session shall talk about this smart materials, and it will consist of 2 modules actually, and right now I am discussing with you the first module. And Professor Suresh Bhalla from IIT Delhi has delivered the lectures for these 2 modules, and he is a world-renowned expert in the field of smart materials and structural health monitoring.
Good morning everyone, and welcome to this introductory lecture on smart materials. Let us see outline for today's talk. We'll begin with smart materials, some of the common types, how they are smart. Then we'll come to the main smart material of focus, that is piezoelectric materials. We'll study their principles, day-to-day utilities, and come down to the use in structural health monitoring. Mainly we'll see 2 applications in structural health monitoring, as dynamic strain sensor and as EMI technique sensor. Then we'll go to futuristic applications and followed by questions and answers. Smart materials are a class of materials which are very special. They possess the ability to change some specific physical property when subjected to a very specific stimulus input. In short, they exhibit stimulus-response characteristics. There are a number of smart materials today available in the market, but in this talk we'll just discuss about 4 major types of smart materials, namely optical fibers, shape memory alloys, electrorheological fluids, and piezoelectric materials. Let us begin with optical fibers. Optical fibers are basically flexible glass fibers of diameters varying from 0.25 to 0.5 mm. They are used for fiber optic communication, and this is the backbone of today's communication in the world. Fiber optic communication, it basically involves transmitting pulses of infrared light through the optical fibers using the process of total internal reflection. Now, why is fiber preferred over electrical cabling? The reasons are 2. Number 1, it provides a high bandwidth, and number 2, this provides immunity against electromagnetic interference. The fibers, they have also been used as sensing elements. There are a number of ways in which optical fibers, they can be used as sensors, but the most common and the popular method is by means of fiber Bragg grating, or FBG in short. So FBG is a set of gratings which are imprinted in a small segment of the optical fiber such that they reflect a particular wavelength of light and they allow transmission of the rest. So if a wide band of light is passed through the fiber, we'll find that maximum of the components, they are transmitted through the fiber, but one particular wavelength, which is called as the Bragg wavelength, is reflected back. Now this Bragg wavelength, it offers us the clue for sensing. So if there is any kind of strain in the fiber resulting from direct stress or from temperature or pressure, the periodicity of the gratings, that changes, and this alters the Bragg wavelength. So this serves as the measure of the particular parameter like strain, temperature or pressure. Now let's come to shape memory alloys. Shape memory alloys, they are very special alloys. One of the examples is nitinol. So the property of these alloys is that they can be deformed at room temperature, but then they return to the pre-deformed memorized shape when heated above a particular temperature called as the transition temperature. Now why this phenomena happens? This phenomena happens because of phase change from martensite to austenite. There are a number of applications in various domains. So very common biomedical application is the insertion of stent to unblock the arteries. So typically in case of patients who have blocked arteries, the process involves insertion of stent, compact shape. Then when it comes in contact with the blood, it expands by undergoing the transition and it unblocks the artery. Similarly, we have a number of futuristic applications. One of the possible futuristic application is damage healing, which is shown by this lab study by a group of researchers, Song and co-workers. So here we see one reinforced concrete beam where shape memory alloys is used as the reinforcement. So typically if the shape memory alloy is heated by means of electrical process, then it would come back to its original shape, say which is straight, and this process will cause damage healing. They also have futuristic applications in structural control and also in aircraft wings. So presently all the aircraft wings, they use flaps to change their direction. But if the shape of the wings themselves is changed, then it will give a lot of benefits in terms of weight reduction and better maneuverability. Electrorheological fluids, they are a special class of fluids which undergo change in viscosity under an electric field. So they have a number of applications like shock vibration absorption in vehicle suspensions, in hydraulic valves, and some of their futuristic applications involve earthquake response control of structures. The phenomena of piezoelectricity occurs in non-centrosymmetrical crystals. The word piezoelectricity means electricity resulting from pressure. Act of stretching or act of compaction causes a net dipole moment in the crystal. So this appears as the development of charges. Now same crystals, they undergo the converse effect also. That is, if they are subjected to electric field, they will undergo strain. Now in this category, there are a number of crystals like quartz, lithium niobate, lead zirconate titanate, which is an alloy of lead zirconate and lead titanate, and then we have lead lanthanum zirconate titanate. Now let's see what kind of smart effects they are exhibited by piezoelectric materials. Essentially there are two effects, direct effect and converse effect. So direct effect means that when subjected to mechanical stress, the piezo materials, they undergo the development of charges. So charges means that this is associated with potential difference which can be measured, and this provides an indication of the stress. Now the same piezo materials, if the stress type is changed from compression to tensile, then we'll have the reversal of the charges. So typically if they are subjected to dynamic stresses, then they will have the charges which are alternating in nature, and so the potential difference or the voltage associated with it will be an alternating voltage. Converse effect, if they are subjected to an alternating electric field, they undergo dynamic elongation contraction, that is, they undergo vibrations, and these vibrations, they can be transmitted to the structures they are bonded with. So the direct effect is used in sensing applications, so they can measure the stress and the strain, and the converse effect, this is used in actuation applications. So if they are bonded to a structure, then we can induce vibrations in the structure. There are numerous applications of the direct and the converse effects in day-to-day life. Direct effect, for example, is used in igniters and detonators to create spark by bringing the two terminals very close to each other when the piezo element is pressed. So the direct effect is also used in accelerometers, tactile sensors, pressure transducers, dynamic strain sensors, mobile phones, the microphone. So essentially the microphone converts sound or the acoustic waves to electrical pulses using the direct effect. They are also used in structural health monitoring and energy harvesting. So energy harvesting is something like this piezo element can serve as a generator. In fact, it's a very compact generator, no moving parts, and it can produce electricity in this fashion if it is under dynamic stresses. Now, as far as the converse effect is concerned, the piezo elements, they are used in mobile phones, the speaker which converts electrical pulses to sound waves. They are used in fuel injectors, musical cards, inkjet printers, vibration control, turbo machinery, numerous kinds of actuators, and precision positioning. There are right now over 200 types of piezoelectric materials available commercially, usually of two kinds, ceramics and polymers. Among the ceramics, lead zirconate titanate is most widely used ceramic. In fact, it is the most widely used piezoelectric material today, though it has high stiffness, but it suffers from the fact that it's quite brittle in nature. Among the polymers, polyvinylidene fluoride, that is PVDF, is very popular. It is ductile, but it has less stiffness. Now, in the commercial market, the PZT, it is available in form of sheets of various thicknesses, various shapes, and various plant dimensions. It is available as square, rectangle, annular rings, but is brittle in nature. So there are some special types. For example, the CVS, which is a special type of piezo composite sensor, and then there is macrofiber composite or MFC and the Duract. So these are special types of sensors. So the concrete vibration sensor, it's basically a cement PZT composite sensor. It is for specific application in concrete structures. It can be very easily embedded at the time of casting. The macrofiber composite is made up of piezo fibers. So this imparts it flexibility of bending. So it can be bent to any shapes, and it can be bonded even on non-straight surfaces. Duract also belongs to the same category. We show you converse effect in the lab. Let us now understand the piezoelectric constitutive relations. So the treatment is a bit mathematical in nature, but if you pay attention, it will be very easy. Let us assume that we have a piezoelectric element of length L along axis 1 with W along axis 2 and thickness H along axis 3. So this element basically it lies in 1-2 plane. Axis number 3 is in the thickness direction. Let us begin with the converse effect. What is converse effect? Converse effect means that if we apply electric field, we will find strains in the piezoelectric element. So we begin with application of stress. So if stress is applied, then the piezoelectric element, it behaves like any other linearly elastic material, and it undergoes the development of strain which is proportional to the stress, being related by the Young's modulus of elasticity. Converse effect, if we apply electric field, then electric field also gives rise to additional strain, and the two effects, the two strains, they are additive in nature. Let's now see the direct effect. Direct effect means that if we apply stress, we see the development of charges. Now for this equation, we assume that the piezo element is under the combined action of stress and electric field. So as a result of the electric field, like all dielectric materials, it will display the development of charges under the action of the applied electric field. Here epsilon 33 with superscript T is the electric permittivity under constant R0 stress. Now on account of the direct effect, there will be additional charge also, that is the stress will give rise to charge. And what we find between the two equations, that we have a common term D31. This is called as the piezoelectric strain coefficient. So here what 3 and 1 they stand for, basically the first subscript, it indicates the direction of the electric field, which is along the axis 3, so we find 3 here. And the second subscript, it indicates the direction of the stress or the strain, which is axis number 1. Now it should be understood here that in the case of the Young's modulus of elasticity, we are using a bar and a superscript E. So the superscript E indicates that the quantity is measured under zero electric field. The bar above the symbol Y, it indicates that it is measured in the dynamic condition. So this is the dynamic Young's modulus, that will be slightly higher than the static Young's modulus. In the case of the electric permittivity epsilon, we find that there is a superscript T. So this superscript indicates that this parameter is measured under zero stress conditions, and similarly the bar indicates that it is pertinent to dynamic condition. Let's now go to the next part, the applications in structural health monitoring. So what is structural health monitoring? It is a very elaborate definition. Let us first read it together and then we'll pinpoint the various components. So structural health monitoring means measurement of operating and loading environment and critical responses of a structure to track and evaluate the symptoms of operational incidents, anomalies, and or deterioration or damage indicators that may affect operation, serviceability, or safety reliability. So this is a comprehensive definition of structural health monitoring coined by Acton and co-workers. So now if we see closely here, the key word is measurement. So what we measure two things. Number one, the operating and loading environment, and number two, the responses of the structure. So these two quantities are measured. And what is the goal? Goal is to evaluate the structure and look for any clues for damage. The concept of structural health monitoring is very similar to the health monitoring of human beings. So the reason is very much similar, that we go for regular health checkup to the doctor at the hospital. So in same manner, structures, they also need structural health monitoring in a continuous manner. By structures, we not just limit ourselves to civil engineering structures, but we also include mechanical systems, machines, aerospace structures, and other kind of material systems. Now here two examples shown here. One is the I-35 bridge collapse in Minneapolis, which occurred in 2007. So here the reasons for the collapse were found to be design flaws, corrosion, overloading, etc. Similarly, this accident in the aerospace industry occurred in April 1988. So what happened that during the flight of Aloha airline, the fuselage suddenly ripped apart. However, the passengers, they were all tied to their seats by the seat belts, so major fatalities, they were averted and the flight could land back. So the underlying cause of this accident was later found to be the appearance of multi-side cracks in the skin joints. These led to the unzipping of large portions of the fuselage. They were undetected during the routine pre-flight inspections. So these two accidents lay emphasis for structural health monitoring of civil engineering infrastructures, mechanical systems, and aircraft. Now the civil engineering infrastructure, they have a lot of vulnerable components. So these kind of bridges where the construction is like there is a suspended span resting on two cantilevers from the two sides. So This is very common. Lot of bridges in the middle of the previous century, they were constructed with this kind of arrangement. So here there are 4 hanger pins which are connecting the suspended span with the cantilever span. So these hanger pins, they are very, very critical in nature. Often these hanger pins, they are undergoing the process of corrosion which remains undetected. So this is very, very critical phenomena because it undermines the safety of the structure. So it's very important to monitor such components in the infrastructure. So we can list some of the reasons for structural health monitoring. The first and foremost is to facilitate life cycle management decisions. So if we have continuous structural health monitoring using the measurements, we can take scientific decisions with regard to the life cycle of the structure. Then structural health monitoring can facilitate design validation. Design of structures is often based on parameters affected by statistical variation and uncertainty. So it's very important that after the structure has been constructed, we validate the design. Then we need structural health monitoring to check the structure after it has undergone a major retrofitting. Visual inspections, they are very difficult, very tedious, they need trained professionals. So if there is an automated system of structural health monitoring, it can go a long way. Finally, structural health monitoring can facilitate generation of a useful database of the structure consisting of the history of external loads, the stress distributions, deflections, and so it can facilitate a long-term understanding the behavior of the structure and can help in various decisions. So when we talk of structural health monitoring by means of piezoelectric elements and in specific by PZT or the lead zirconate titanate, which is the most widely used piezoelectric material, then there are 2 modes. One is as dynamic strain sensor. This uses direct effect and it operates under low frequencies. The other is the electromechanical impedance technique based sensor. This uses both the direct and converse effects and it typically operates at high frequencies. So direct effect means just for sensing, converse effect means for actuation. Direct and converse effects together mean that we use both for sensing and actuation. So let's go to the first mode, that is dynamic strain sensor. So we just derive a simple equation for potential difference across the terminals of the PZT patch if it's under dynamic stresses. So we make use of the equation of the direct effect. So if there is no external electric field, then we have a simplified equation, and if we use the common equation for parallel plate capacitors, that is charge is equal to capacitance multiplied by the potential difference across the 2 terminals, then we can derive a very simplified equation between the potential difference and the strain. So that means voltage is directly proportional to strain, and if we here input the values of various parameters for a typical piezo ceramic material like lead zirconate titanate of commonly occurring grade, we'll find that we are getting a sensitivity of typically 200 millivolts per microstrain. So this constant K has typical value of 200 millivolts per microstrain. So here H is the thickness of the PZT patch. So it should be noted that the PZT patches, they are suitable for dynamic strains and they are not suitable for static strains. The reason is that piezoelectric effect is dynamic in nature, that is the charges are generated when the forces they are changing or the stresses they are changing. If we have only a static force, then what will happen? The initial charge will decay in the circuit and then the voltage difference or the potential difference will go down to 0. So they are not suitable for static stresses. So typically in the case of the dynamic strains, we have found through our experiments that frequencies as low as half or 0.5 Hz, they can be easily measured by PZT patches. Now we are taking you inside our lab to show you the sensing application, that is the direct effect.
So in this session we covered the definition of smart materials and the various types of smart materials and their applications. In addition to this, the concept of structural health monitoring was also given. Further focus was on the piezoelectric smart materials and its application for SHM. We saw that the constitutive relations for piezoelectric material and its converse and direct effects were very well discussed. At the end of the lecture, practical demonstration of the direct and converse effect of piezoelectric material was also shown. Thank you very much.